Alright, so imagine we had the following problem. We were asked to find the greatest common divisor of these two numbers. And from the technique we learned, or we reviewed in the last couple of videos, coming up with a prime factorization of these two numbers would take a long time. It would be a lot of work. So let's see if we can use some knowledge that we already have and one more result that we'll have to prove to come up with an easier way of finding a greatest common divisor. So I just want to come up with a few results here. So the first one that's going to be important is take any counting number that you like. The greatest common divisor of that number and 0 is the original number. Remember, everything is a divisor of 0. Everything is a factor of 0. So n times 0 is 0. N times 1 is n. So the greatest common divisor of n and 0 is n, for any n here. That's going to be really important to us. The second thing I want to, this is more of a reminder than a result, and it is the following thing. It is that if you have two whole numbers, or I should say two counting numbers, and let's say a is the bigger one if there is a bigger one, maybe they're the same, then you can write a divided by b as q remainder r, which is the same thing as saying a is q groups of b plus this remainder r, where, and this is going to be important to us, where r is not negative, it's 0 or greater, but it's strictly less than your divisor b. Your remainder is smaller than your divisor. That's going to be important to us as well. And the final result that's going to be important to us, and this we're going to have to do a little bit of work to show that it's true. But if we have two counting numbers where a is the bigger one if one is bigger, then the greatest common divisor of these two numbers is the same as the greatest common divisor of b and the remainder, where a you can write as q groups of b plus a remainder. And let's say where, of course, your remainder is strictly smaller than b, and it's not negative. And if we think about that, what's happening here? Well, if there is a bigger number between a and b, a is bigger than b. And we know b is bigger than r. So if we take this problem, if we can prove this result, which we will in a second, then we're turning this greatest common divisor of a and b into a problem with smaller numbers. The greatest common divisor of b, which is smaller than a, and r, which is smaller than b. So we're making the problem smaller. And what's nice is, well, we could just do this again. We could keep iterating this and then we'll do to figure out what the r is, like we did for a and b, to figure out what the remainder is. Just do the same idea again. Do b divided by r, get a new remainder, and just keep iterating that process. And if you think about it, and this is very important, the remainders are going to keep getting smaller. The remainder is always smaller than your divisor. Because it's always smaller, it's going to go down and down but it can't get smaller than 0. Eventually, it will have to reach 0. So if we kind of use this result as much as possible, then eventually we'll get to the situation where we're taking the greatest common divisor of some number and 0. And we don't even need to do any calculation with that. The answer will just be that number. And that's basically the Euclidean algorithm. We just use this result over and over again until we get to the case where we have our divisor here as a 0, and then, well, the greatest common divisor of n and 0 is, of course, n, and we're good to go. And this isn't really, I shouldn't say it's a divisor because you can't divide by 0. But when your second smaller number is 0, then you know that the greatest common divisor is going to be the other number. But we need to show this. It's not too bad. We have all of the techniques available and all of the knowledge to be able to show that this is true. All right, so let's see if we can prove this result. Let's call D for divisor, I guess. Let's let D be the greatest common divisor of our two numbers. So that means D is a factor of A, and D is a factor of B, and D is the largest such value. All right. So we're just going to call D the greatest common divisor. Now, remember, by the quotient remainder theorem, we can write A as Q copies of B plus some remainder. For, I should say for Q, not B, for Q and R, which are some whole number. And R is a remainder, so I better tell you that it's for sure less than B, strictly less, and it's greater than or equal to 0. It's some remainder. Okay. So, let me call this star here. I'm going to call this equation star. So I'm going to rearrange star for R. So rearranging star for R. So I'm going to subtract QB from both sides. So let's look at this. What do we have? We have that A minus QB equals R. So, if we look at this, well, we know D is a factor of A. It's the greatest common factor. D is a factor of B, so by Theorem 1, D is a factor of QB. But we have two terms here where D is a factor of both, so D is going to be a factor of the difference. So Theorem 2 says D is a factor of both. So I'll just write it in. By Theorems 1 and 2, D is a factor of A minus QB. But A minus QB equals R. That equals the remainder. So since A minus QB equals R, well, D must be a factor of R. Well, since D is a factor of R and D is a factor of B, because remember, D was the greatest common factor of A and B, so it's a factor of both, and we know D can't be any bigger. If there was a bigger factor of R and B, then it would also be a factor of A, since it would be, you could use theorem 2 here. If there was a bigger factor of B and R, then it would also be a factor of A. So this tells us, so D must be the GCD of B and R. So that's really cool. So we get that the greatest common divisor of A and B is the same as the greatest common divisor of B and the remainder R. Fantastic stuff. All right, so now that we have that result, let's talk about the Euclidean algorithm, which uses these three facts. So basically, how this Euclidean algorithm works, and it's called the Euclidean algorithm because it's named after a Greek mathematician from way back in the day, probably 3,000 years ago, named Euclid. Euclid wrote a book called The Elements, which is the second most published book in the history of the world after the Bible. So it's a very, very important book on mathematics. And one of the things he talked about in his book was the Euclidean algorithm that we're doing here. So, what this is, basically, we're just going to apply result 3, which we just proved, over and over again. We say iteratively in mathematics. We're going to apply that result iteratively. And I just realized that I wrote this incorrectly. It should be iteratively. Iteratively. There we are. That looks better. So we apply the result over and over again. We just keep doing that long division and keep taking remainders until we're in the situation where we have one of our remainders being 0, and then the GCD is just the other number, which is going to be our previous remainder. And result 3 tells us that that answer is the GCD of our original numbers. So let's do our example that we had at the start of this video. It was the greatest common divisor of 2,716 and 9,478. Okay. So, we need to do a little long division here. So 2,716 into 9,478. I'm always putting the bigger number as the dividend and the smaller number as the divisor. So it looks to me like it goes in 3 times. So 3 times 2,716. So 18, carrier 1. 3 times 1 is 3 plus 1 is 4. 3 times 7 is 21, carrier 2. 3 times 2 is 6 plus 2 is 8. And we subtract 0, 3, 3, 1. So we get a remainder of 1,330. So we simplified this problem into the greatest common divisor of 2,716 and 1,330. So this is a necessarily smaller problem than this one, but we can just apply the same thing. Let's do it again. So we're going to take 1,330 and see how many times it goes into 2,716. It goes twice. 0, 6, 6, 2. We subtract 6. We borrow 5, and that's it. So we get a remainder of 56. And you can see this problem gets even smaller. That's what do we have? That's going to be 1330 and 56. Okay, let's do it again. How many times does 56 go into 1,330? Well, 56 goes into 133 maybe twice. We subtract, we get 112, sorry. There we are. Subtract, we get 210. All right. And then 56 into 210 goes maybe 3 times. Let's see. 3 times 6 is 18. Carrier 1. This is 16. And we subtract. Minus 6 is 4. And I forgot to do that. So it's 42. Okay. And now we've reduced this problem to the greatest common divisor of 56 and 42. Now I will say the following thing. So we could continue this algorithm. In fact, I will continue this algorithm. But at any stage, we can calculate the GCD in a different way if we choose. So if you wanted to, you could do a prime factorization of 56 and 42 now and figure out the GCD that way. But just to see how this algorithm ends, we might as well finish this off. In fact, I'm just going to erase this bit here. Since this is a video, you can always rewind if you want to see what I erased. So I'll erase all of this, in fact. So we need 56 and 42. So 56 and divided by 42 goes obviously once. And we subtract, we get 14, so we have a remainder 14. So this is the same thing as the greatest common divisor of 42 and 14. So how many times does 14 go in to 42? Well, it goes 3 times. Oh, with a remainder of 0, with no remainder. So this is the same thing as the greatest common divisor of 14 and 0, which is, of course, 14. So, after simplifying that problem a whole bunch, we get that the greatest common divisor of what we started with, 9,478 and 2,716, is 14. So that's how the Euclidean algorithm works. And thus you have another technique of finding a greatest common divisor, especially if your numbers are a little bit bigger. This will come in handy for us a lot when we talk about fractions. If you think about it, if we want to simplify a fraction, we want to divide the numerator and denominator by the greatest common divisor. So if we have a fraction with a very large numerator and denominator, we can apply something like the Euclidean algorithm to figure out what we need to divide the top and bottom by to simplify it. So let's look at one more example. So let's try and find the greatest common divisor of 785 and 554. So I think it's a good idea for you guys to stop the video now and try this yourself. So pause the video and see if you can come up with the greatest common divisor. And we'll talk about the answer, because the answer is a particular type of answer. Okay, now that we're back, again, we're just going to apply the Euclidean algorithm just like we did in the previous example. So 554 into 785 goes once. We subtract, we get 231. So this is the same thing as the greatest common divisor of 554 and 231. We do more long division. 231 into 554 goes twice, so that's 462. Subtract, we get 92. So our remainder is 92. So this is the same thing as the greatest common divisor of 231 and 92. Just to make sure, it's always going to be the divisor and the remainder that go in your GCD calculation. So we'll do it again. 92 into 231. So it goes twice. That's 184. We subtract. We get 7. So that's 47. Okay. So the greatest common divisor of 92 and 47. Now, if you're astute here, you would realize that 47 is a prime number. There are no factors of 47 besides 1 and itself. 92 definitely isn't a multiple of 47, because 47 times 2 is 94. So there are no prime factors in common here. So just realizing that, I could stop the calculation right now and say, well, I know the greatest common divisor. Well, there's only 2 divisors of this number, 1 and 47, since it's prime. 47 isn't a factor of this guy, so the greatest common factor, or the greatest common divisor, must be 1. So these numbers here have a greatest common divisor of 1, which means they share no prime factors whatsoever. And in that situation, numbers that have no prime factors in common, that have a greatest common divisor of 1, we call coprime. Or relatively prime is another way of saying it. They share no prime factors. So that's pretty cool. I will say, you could continue the calculation. I'm not going to do it, but you will end up with the step where you get the greatest common divisor of 1 and 0, which of course would give you 1. So you could continue this calculation just doing the same process over and over again, and you would end up with this line at the end, and the greatest common divisor would be 1. But if you can see at a certain step that the greatest common divisor is going to be something, you might as well stop there and just do it. If you notice one of the numbers is prime and the other number doesn't have that prime as a factor, well, it's pretty easy to say that the greatest common divisor then must be 1. So that's how the Euclidean algorithm works. If you practice it a bunch, it's not particularly difficult. It's just a few steps. Kind of the key thing is that result 3 that we talked about. That's the key to all of this. We can simplify the greatest common divisor calculation by realizing that the greatest common divisor of A and B is the same as the greatest common divisor of B, and the remainder when you divide A divided by B.